Hello, this video covers chemical bonding. So what exactly is bonding? Bonding is any type of force that holds atoms together so they can function as a unit. Bonding can come in two types. It can be ionic or covalent. So when we talk about ionic bonding, we're dealing with an electrostatic force between two particles carrying opposite charges. In other words, positive charges attract negative charges in ionic bonding. Covalent bonding occurs between sharing of electrons using overlapping orbitals that cover both atoms. And there is some area in between ionic and covalent bonding. So let's focus first on ionic compounds. Compounds that are composed of ions are called ionic compounds, and sometimes they're referred to as salts. They contain a metal cation, or a positive ion that was formed from a metal atom, combined with a non-metal anion, or a negative ion that was formed from a non-metal. The ions form in the ionic bonds, and then the attraction between the positive and the negative ions, it's what holds those ions together in an ionic bond. So here's a sample of sodium, which is a soft reactive metal, and a sample of chlorine, which is a pale yellow poisonous gas. And when they react together, they form a white crystalline solid called sodium chloride. Now, ionic compounds have typically high melting points. That means their electrostatic forces are really strong. They tend to form crystalline structures, which are just highly organized patterns of what are called unit cells. And they're poor conductors of electricity. However, if we were to dissolve an ionic compound in water, the ions are free to float around in that solution, and then they become excellent electrical conductors. Now, the strong electrostatic attraction between a sodium ion and a chloride ion is what holds them together tightly in the ionic compound sodium chloride. And it requires a lot of energy to break up a sodium chloride unit. So if we have solid sodium chloride, we would have to add in a lot of energy to break it up into its sodium ions and its chloride ions. Now, this is an example of what the structure, the crystalline structure of sodium chloride looks like. And if we look, there are a lot of these electrostatic attractions between the sodium and the chloride ions. So the ions in sodium chloride are arranged to maximize opposite charges interacting. And if we look, we would see that each ion is surrounded, in this case, by 8 other ions, meaning they're going to be very strong interactions. So how do we know what the ion ratio is in salts? When we look at salts, they are electrically neutral. That means the total positive charge must equal the total negative charge. So that won't always be a 1-to-1 ratio in salts. So if we were to look at this as an example, we have an aluminum ion, which has a +3 charge, and we have an oxide ion that has a -2 charge. In order to make the charges equal, 3 and 2 have 6 in common. So we would need 2 +3 aluminum ions for every 3 -2 oxide ions to make our whole compound electrically neutral. Now, here's a trick. If we take the number for our cation and drop it down here and write it as a subscript for the anion, and take the number up here for our anion and switch it down here and make it the subscript for our cation, that will always give us a neutral ionic compound. So the 3 would come down here, the 2 would come down here. The formula for aluminum oxide would be Al2O3. So we have 2 aluminum ions, each with a +3 charge. That gives us an overall charge of +6. And we have 3 oxide ions, each with a charge of -2. That gives us a charge of -6. +6 and -6 cancel each other out, and we have a neutral ionic compound. So let's look at this example. We've got a magnesium ion with a +2 charge, and we've got an oxide ion with a -2 charge. Again, we'll take that 2 from the magnesium and drop it down here, and the 2 from the oxide and drop it down here. But we're never going to have anything other than a simple ratio in our formulas. So Mg2O2 can be simplified to MgO. So if we have 1 magnesium with a +2 charge and 1 oxide with a -2 charge, that gives us an overall neutral charge in our compound. What are common ions and their charges? Well, we know that elements that are in this first group here are called alkali metals. They tend to form ions with a +1 charge. Here in this second group are alkaline earth metals. They tend to form ions with a +2 charge. When we look over here at group 3, they tend to form ions with a +3 charge. Now notice these are all positive. Metals tend to lose electrons and form positive ions or cations. Now the transition metals tend to form more than one type of ion, but we need to know that silver always forms a +1 charge. Zinc and cadmium always form a +2 charge. Now over here on this side, we're going to be looking at our nonmetals. If we have elements that are in our nitrogen group, they will always form a -3 charge. The oxygen group will always form a -2 charge. Our halogens will always form a -1 charge. And our noble gases actually have a stable electron configuration already, so they don't ever form ions. And again, if we were to look at the nonmetals, they tend to form negative ions because nonmetals tend to gain electrons. So we've got our metals here that tend to form cations, and we have our nonmetals here that tend to form anions. The transition metals tend to have more than one possible type of ion they can form. So let's look at the electronic structure of ions. But where do the common charges actually come from? How do we know that alkali metals will always form a +1 and halogens will always form a -1? It has to do with their electron configuration. If we look at sodium and calcium and aluminum as examples of metals, their shorthand electron configuration would be neon 3s1, argon 4s2, and neon 3s2, 3p1. Sodium has 1 valence electron, so it tends to lose that 1 valence electron in order to form a noble gas electron configuration, which would be stable. And in losing an electron, the sodium atom becomes an ion with a +1 charge. Calcium has 2 valence electrons. It's going to tend to lose those 2 valence electrons in order to form a stable electron configuration. And in doing so, it's going to form a +2 charge. And if we look at aluminum, it has 2 + 1. It has 3 valence electrons. And if it loses those 3 valence electrons, it will have a stable noble gas electron configuration. And in losing those 3 electrons, it's going to form an ion with a +3 charge. So metal atoms tend to lose electrons in order to form stable electron configurations. And in doing so, they form positive cations. Now, nonmetals like chlorine, oxygen, and bromine tend to gain electrons. So if we were to look at chlorine, it's neon 3s2, 3p5. It has 7 valence electrons. If a chlorine atom were to gain 1 electron, it would then have the electron configuration of argon. And because it gained 1 electron, it's going to have a -1 charge. Oxygen is helium 2s2, 2p4. It has 6 valence electrons. So if an oxygen atom were to gain 2 electrons, it will have a stable electron configuration, and its charge would be -2. Bromine has an electron configuration argon 4s2, 3d10, 4p5. But remember that valence electrons are in the s and p orbital, so we have 2 electrons here plus 5 electrons here. Bromine has 7 valence electrons. If it gains 1 electron, it's going to have a stable electron configuration, and the charge on the ion would become a -1. So what about transition metals? Okay, transition metals, remember, have an s and a p orbital at the end of their electron configuration, but the electrons in the s orbital are always going to be removed before the electrons in the d orbital. So let's look at some of these ion ratios in salts. So if we have a potassium ion and a calcium or a carbonate ion, the 1 from the calcium would get dropped down here, and the 2 from the carbonate would get dropped down here, and our formula would be K2CO3. Aluminum has a +3 charge, chloride has a -1 charge, and if we crisscross those numbers, our formula becomes AlCl3. Calcium hydroxide, we've got a +2, which would drop down here, and a -1, which would drop down here, and our formula would be CaOH2, but we want to put parentheses around the OH to show that there are 2 hydroxide ions for every 1 calcium ion. So next we have a +1 and a -3. We want to crisscross the numbers. So we get Na3PO4 for our formula. Next we have a +2 and a -3. So the 2 from the magnesium would drop down here, and the 3 from the phosphate would drop down here. And because we want to show that there are 2 phosphates, we need to put parentheses around this ion. For this one, we've got a +1 and a -2. So we crisscross the numbers and we get NH4,2SO4. We want to show 2 NH4s and 1 SO4. Now let's look at covalent bonding. Covalent bonding occurs when atoms share pairs of electrons. The sharing of electrons enables both atoms to have a full shell electron configuration without having to actually gain or lose electrons. We typically call covalent compounds molecules. So H2 is an example of a covalent molecule. It's 2 hydrogen atoms that are bonded together by sharing a pair of electrons. If we wanted to break that covalent bond, we would have to add energy in order to do so. So how does it work? Hydrogen is H2. Well, each hydrogen only has 1 electron, so its electron configuration is 1s1. If they overlap energy levels, now each hydrogen is sharing a pair of electrons between the two, and that makes that molecule stable. Covalent compounds typically have low melting points and low boiling points. That doesn't mean that covalent bonds are weak, though. It means that the forces that are holding the individual molecules together, which we refer to as intermolecular attractions, are weak. Here we have two atoms. We've got our nucleus here and our nucleus here, and we have our electron cloud outside the nucleus here and our electron cloud outside the nucleus here. There are several different forces in play. The electrons here are going to be attracted to the nucleus here. The electrons here are going to be attracted to the nucleus here. And at the same time, this nucleus is going to repel this nucleus. And these electrons are going to repel these electrons. So it leads us to a graph that looks something like this. If we were to have two hydrogen atoms that are sufficiently far apart, there's no attractive force between those hydrogen atoms. But as we move them closer together, the attractive forces begin to increase and the overall energy decreases. Eventually, we get to this low point here. This is the optimum distance, which maximizes the attractive forces and minimizes the repulsive forces. This would be considered our internuclear distance or our bond length. Now, if the atoms continue to move close together, now the repulsive forces are going to be increasing the energy. So the atoms are too close together here. They're not close enough together here, but they're at their ideal distance here. How do shared electrons give full shells? So again, if we were to look at hydrogen, hydrogen has one proton in its nucleus, it has one electron outside its nucleus. It's not a stable atom by itself. But if two hydrogen atoms were to overlap their energy levels and share a pair of electrons, now both atoms have two electrons between them, and that makes them stable. It's sometimes referred to as the duet rule. Now let's look at fluorine. Fluorine has 9 protons in its nucleus, 2 electrons in its first energy level, and 7 electrons in its second energy level. If two fluorine atoms overlap their energy levels and share a pair of electrons, now they're going to end up with 8 valence electrons. And for most atoms, that gives it stability. The tendency of main group atoms to share enough electrons to obtain 8 valence electrons is known as the octet rule. And again, most atoms tend to do that. So what do we mean when we talk about nonpolar and polar covalent bonds? Nonpolar covalent bonds occur when two identical atoms share electrons. They're going to share the electrons equally between them. So if we had 2 chlorine atoms, they're going to share a pair of electrons equally between them, and we'll have no positive or negative end to that molecule. We refer to that as being nonpolar. If we have a polar covalent bond, it means that 2 atoms are sharing a pair of electrons, but they're not sharing the pair of electrons equally. One of the atoms has a greater attraction for the electrons than the other. If we were to look at hydrogen and chlorine, if they share a pair of electrons between them, both the hydrogen and the chlorine will become stable. But chlorine has a higher attraction for electrons than hydrogen does. The electrons get pulled closer to the chlorine, and we end up with a partial positive end to the molecule and a partial negative end to the molecule. That's what we mean when we talk about polar covalent bonds. When we have poles, a positive end and a negative end, due to the unequal distribution of electrons. Now, ionic bonds are kind of the extreme of polarity. Here we have a sodium atom. It's going to donate its electron to a chlorine atom. Sodium becomes an ion, chloride becomes an ion, positives attract negatives, and now we're looking at an ionic bond. So this is not considered to be a covalent bond at all because it's got a transfer of electrons, but it's kind of the extreme of polarity. So polar bonds lead to what are called molecular dipoles. So the uneven distribution of electrons lead to the unequal distribution of charge within the molecule, and we call that a dipole. The end that's slightly negative will have the greater attraction for electrons, and the end that's slightly positive has a smaller attraction for electrons. So if we were to look at hydrogen and chlorine, again, they're sharing a pair of electrons, but they're going to share that pair of electrons unequally. That's going to give us a dipole in the molecule. Chlorine is going to be more negative than hydrogen is. We can draw that with an arrow. The arrow will always be pointing towards the atom that has the greater attraction for electrons, the more negative end of the molecule. And you're going to have this little plus sign on the opposite side of your arrow. You can kind of think of that as being the side that's going to be more positively charged. Or we could draw it as an electron density map where you would show regions of high electron density and regions of lower electron density. It all has to do with electronegativity, which we talked about in the periodic trends section. So as a review, electronegativity is a measure of the tendency of an atom to attract electrons. A greater difference in electronegativity means more polarizing distribution of electrons, which means we're going to have larger partial charges on the atoms in that molecule. When we look at the periodic table, we have a trend. We know that electronegativity increases as we go across a period, and electronegativity decreases as we go down a group. So the least electronegative elements are down here in the lower left. Fluorine is the most electronegative element on the periodic table. Electronegativity and electron affinity are not the same. Electron affinity is actually a measurable physical quantity. It deals with the energy that's released or absorbed when a gaseous atom acquires an electron, and it can be measured in kilojoules per mole. So if we have a gaseous atom and it gains an electron, it becomes a gaseous ion, and the energy associated with this change is what we mean when we talk about electron affinity. Electronegativity describes how tightly an atom attracts electrons. It's dimensionless, and it's a value that is calculated, not measured. Pauling came up with an arbitrary relative scale for electronegativity going from 0 to 4. Now, there are other scales of electronegativity. So if you look them up on the periodic table and you see values that don't match 0 to 4, it's just a different relative electronegativity scale. How is electronegativity and bond type related? So let's look at the electronegativity difference between two atoms. If the difference is 0, both atoms have the same electronegativity. They're going to share pairs of electrons equally, and we call that a pure covalent bond or a nonpolar covalent bond. If there's an intermediate difference in electronegativity, the atoms are going to share pairs of electrons unequally, and we would have a polar covalent bond. And if there's a large difference in electronegativity, there'll actually be a transfer of electrons from the metal to the nonmetal and form an ionic bond. So as we go from 0 to 4 for our electronegativity differences, the covalent character decreases and the ionic character increases. As electronegativity differences increase between two atoms, the bond becomes more ionic. So generally speaking, if the difference in electronegativity is less than 0.4, it's considered to be a nonpolar covalent bond. If it's between 0.4 and 1.8, it's a polar covalent bond. And if it's greater than 1.8, it's an ionic bond. Now, there are lots of exceptions to this general rule. As an example, HF has an electronegativity difference of 1.9, while NH3 has an electronegativity difference of 0.9. They're both considered to be polar covalent bonds, even though they fall outside of this range. Sodium chloride has an electronegativity difference of 2.1. Manganese diiodide has an electronegativity difference of 1.0, but they're both ionic bonds. Generally speaking, anytime a metal, something on the left side of the periodic table, reacts with a nonmetal, something on the right side of the periodic table, we're going to form an ionic bond. And generally speaking, anytime two nonmetals react together, two things on the right side of the periodic table, they're typically going to form a covalent bond. Can you be covalent and ionic in the same molecule? The answer to that would be yes. Some compounds have what are called polyatomic ions in them. Those are ions that contain many atoms. Sodium carbonate's an example of that. Carbonate is a polyatomic ion. It's made out of carbon and 3 oxygens. And the 3 oxygens are bonded to the carbon with polar covalent bonds. Carbonate has a -2 charge, and the sodiums each have a +1 charge. So the attraction between our positive sodiums and our negative carbonate would be an ionic bond. Ammonium chloride is another example. Ammonium is a polyatomic ion. It contains a nitrogen and 4 hydrogens. The hydrogens are bonded to the nitrogen by polar covalent bonds. But this overall polyatomic ion has an overall +1 charge. If it's associated with a chloride ion, which has a -1 charge, there'll be an attraction between the -1 on the chloride and the +1 on the ammonium, and that would be an ionic bond. So we can see molecules that have both covalent and ionic bonds within the same structure.